So as promised, I want to talk about this very important step in doing crystallography, something that you should pay good attention to, because if you don't have a good crystal and you don't select a good crystal for your experiment, you suffer later. There's no doubt about it. This is such an important first step. So I'm going to tell you some of the things that have worked for me, and then I would welcome your comments about what does and does not work for you. So some of these are sort of warnings about things you should not do that you may not think about before you think about the actual crystallography aspect of it. Because, certainly we're not just making powders. We want good-sized crystals, not too big if they have absorption effects, as I mentioned yesterday. The bigger the crystal, the less the transmittance of the X-rays through the crystal, if they have a tendency to do that, depending on the contents. Okay, so let's just do this here. Nope, it's not turned on. All these devices. Okay. So some of these are the common methods, which you're probably all aware of. You dissolve your solute in a solvent, and you simply cool it, and in a beaker or a vial. You wait and wait and wait. Maybe slow evaporation occurs. This is not really the best method. I'll tell you why. Because the solvent-solute mixture, which we call the mother liquor, is really protecting the crystal from losing anything like a solvent that's been incorporated into the structure. As soon as you remove that solvent, then it starts probably to evaporate, because most solvents are loosely held in the crystal. Then the crystal will crack, and it'll stick to the sides of the vial. You've probably seen this. You try to get it out, it just crumbles, and nothing left. So, and the crystals tend to grow above the surface of the evaporating solvent, right? So they're all stuck there around the sides of the glass. This is not really a good way to grow crystals for crystallography. Maybe it's okay for OChem, I don't know, but it's not a good method. So we'll talk about some alternatives. If it's air stable, it doesn't incorporate a solvent, maybe it's okay. Sometimes you can release them from the sides by just kind of sloshing some of the mother liquor against them, and then they fall down, and then you can get them out. But if you try to poke them out with a needle, you do run the risk of crushing them and losing them entirely. Okay, so hanging drop, that's also an old classic method, where you start with some crystal and you put it in a solution of the substance, and then as it hangs there, maybe by a nylon thread or something, the crystals will grow. That's a really cool way to grow crystals. Big crystals for children. They like to see the crystals growing. But not necessarily the best for crystallography. This method, the slow diffusion of two components in a jar or tube, is probably my favorite method. Now, I'll show you some examples of that. I have had some successful crystal structure determinations from the melt, which really surprised me. But some things will melt, and as the melt cools, the crystals grow, and the melt is just kind of the mother liquor. Okay, that's pretty interesting. Sometimes you get more than one substance, but you could pick out what you want. Grinding is another sometimes successful method, and it's solvent-free. You just take your, say, the components of your reaction, grind them together. A long time, granted, but eventually crystals grow, and people who do materials chemistry sometimes do it this way. That also can just produce a reaction. I'll show you an example of that. Sublimation is kind of an old traditional way, and probably not too useful for you kinds of compounds, but there is some glassware that exists for doing that. Depending on what you have, it might be a good method. So you start with the solid, kind of warm it up, let it sublime, and then it cools, condenses on some kind of cold finger. And sometimes if you do that the right way, you get crystals growing. I list this because there was a person who was in our department at one time. He isn't there now, but he was experimenting with supercritical CO2, and we grew crystals from supercritical CO2. But not every compound is useful for that. These tended to be fluorinated compounds, and they worked really well. And that was, again, it's a green method. You don't have any solvents to dispose of or anything. CO2 just goes into the air, and that's it. Convection or zone crystallization, I'm explaining here that the solution is saturated. There's some kind of way of circulating this so that the solution containing the desired material is moving away from that solution and maybe crystallizes on a glass to the side. There's special devices for doing that. And again, that's pretty old, traditional way of doing things. But if you have the apparatus, it's worth trying. I didn't actually draw you a picture of that apparatus, but it used to be done in our lab 50 years ago. Hydrogen transfer, I really need a picture to explain that, so let's just go on and I'll show you what that means. So solvent considerations. You want to avoid supersaturation because, of course, the crystals will grow too fast if it's supersaturated. Once they're initialized, once the crystallization is initialized, they tend to just crash out. So it's concentrated but not supersaturated. Looking for appropriate solvents. I don't need to tell you guys that like dissolves like. So, if your material is very polar, then you want sort of a polar solvent. If it's nonpolar, then maybe a hydrocarbon solvent. That kind of thing. If there's a potential for hydrogen bonding, you might want to think about what could result from a hydrogen bonding interaction. Would it be between your molecules, or would it be between your molecules and the solvent? Sometimes it helps, and sometimes it prevents them from crystallizing. So this is something you have to experiment with to see if that makes sense. I would avoid methylene chloride and methanol because they're very volatile, surprisingly, unless you can absolutely be sure that you're keeping your crystal cold before you take it out of the mother liquor and before it ends up on the diffractometer, because they'll evaporate so fast from crystals that you often get cracking. Of course, methylene chloride is an excellent solvent, and so sometimes you want to use it anyway. You might be tempted to use a long chain alkyl solvent like heptane, N-heptane, or something like that. But you're asking for disorder if it is incorporated in the crystal, because usually long chain hydrocarbons, they start wobbling at the end, at the long end, and then it's hard to model. And they end up in kind of strange ways in cavities in crystals. That said, you may find that it works. You have to just try a lot of different things. I really do prefer solvents with sort of rigid geometries because it's easier to model a disordered solvent with a rigid group. Something that I want to talk to you about later. Like toluene tends to be disordered, but it's easy to model because you can incorporate rigid groups to do that. And if it's a floppy molecule, you can't use the rigid group method for modeling disorder. Benzene is good. You really have to just do a lot of experiments. But try not to use too many solvents, because if you've crystallized with 3 different things, 4 different things, they may all end up in the crystal, but some of them on top of each other. For example, chloroform fits pretty well on top of benzene. So if you have both of them in there, you got another disordered problem. 2 things right on top of each other. Okay, you can model it, but it's a pain. It takes more time than solving the main structure. So try to keep it to 2 solvents or less even. Sometimes you'd only need 1. Okay. So mechanics. Okay, this is. It would be wonderful if we could actually watch crystals grow at that, at that submicroscopic level and see what's going on. But we do know that they grow by the ordered deposition of the solute molecules onto the surface of some nucleation crystal, some pre-existing crystal. Classically, we have always said that purity assists in this process, although I confess that over time, sometimes we've grown really nice big crystals just from the reaction mixture. We didn't actually bother to isolate the product, weigh it, which you should do, of course, get your yield, and then recrystallize it purified. Sometimes you get a really nice crystal just from the reaction mixture, but you still need to go back and figure out what your yield was, so yeah, don't throw it away. It is probably a good idea to remove particulates. So you can do this in various ways with microfilters or just putting it through smashed up Kim wipe or something to get the particulate matter out. But once you've set up your crystal growth vessel, make sure it's not near something that's vibrating a lot, because it's better, they grow better if it's still. So I would put the crystallization apparatus in a closet away from pumps, away from people who are going to slam doors. So keep vibration down. Rotovaps, you'll never get crystals next to rotovaps, I don't think. Hoods aren't so good either, even though you're tempted to put them in the hood where you can see them once in a while. There's just a lot going on around a hood. It's better to put them away and try to forget about them. Every time we go away for like Christmas vacation, we come back and everybody has crystals. Why? Because they're sitting there and nobody's looking at them. So if you do pick them up and look in the flask, do it gently, don't shake it, keep it still as you can. These are all my words of advice. You may have already discovered these. So sometimes the fullerenes that I study a lot, and I'll talk about those this afternoon, take as long as 2 months to grow. So be patient. Some things take a long time. I'll give you an extreme example here at the end. So time can be a long time, longer than you want to wait. That's the way it goes. So now you've looked at your vial, you've decided there's something interesting in there, like you can see some crystals. Once you do remove them, if you're going to be bounding the crystal yourself, now maybe you won't be, but if you do, you want to get them onto the diffractometer fast, usually with a cold stream, because you're not only fighting possible decomposition, but you're fighting thermal motion, remember. So data collection at low temperature is always better. But it'll also keep your crystal from any decomposition, loss of further solvent, etc. If the technician says, oh, our apparatus is broken, ask him when it's going to be fixed. Wait. Get the cold stream going. Okay, I already said that. Yeah, so if it's really unstable and you have only seconds to get your crystal on, I have a really quick and dirty method of doing that. So I get a big petri dish about this big. Crush some dry ice. Spread the dry ice around the circumference of the circle on the inside of the petri dish, but leave enough space for a slide in the middle. Then put the slide in, take a squeeze bottle and make a circle of the viscous oil that you're using, whether it be Proton oil or something else. Then with a pipette, drop your crystal together with some mother liquor into the middle. Okay? And it's going to get cold pretty fast because of all this dry ice. Maybe swirl it around a little bit to coat the crystals. And try to pick one out within a minute, say. If you wait too long, the dry ice may actually make the oil too viscous, and then it's really hard to get the crystal picked out. But to keep it there with some of its mother liquor is really valuable. A lot of the students will call me, if they've got this situation, they call me down, because I'm really good at that. But I also am very good at spotting a good crystal very fast. And I'll point out some more tips about that too. Some people have actually used a nitrogen cold stream to mount their crystal and carry it over to the diffractometer and get it into the diffractometer's cold stream. I find that very, very difficult. I don't actually use that method, but some people do. You probably need some kind of special apparatus to do that, though. You can't just have somebody hold a cylinder of liquid nitrogen for you. It's tricky. All right. Okay, so purify your compound, like I said. I'm wondering sometimes if that's necessary. Certainly that is the long-standing recommendation. But if you know that it's thermally sensitive, and if it's air sensitive, consider all of those things. Solubility profile, do you know what I mean by that? Sort of do some preliminary experiments, if you have enough material anyway, to see what it's soluble in, what it's sparsely soluble in, what it's insoluble in, so you know what you're going to be trying. Use clean glassware, of course, because if you don't, you have nucleation sites where you may get small crystals growing, but not big crystals. And set up several things at the same time, different ratios and so on, molarities. See what works. Some people say growing crystals is an art, not a science. Some people seem to be particularly good at it, that's for sure. Yeah. Some crystals are sensitive to moisture, and some crystals lose moisture. A lot of crystals that contain water, if they were crystallized from water, lose the water pretty fast. Just, keep an eye on it. Okay, I said most of the first three things there. Do you have a sonication apparatus? You can get a more concentrated solution with sonication. That's a good idea because you don't want to have insoluble material floating around. If you do, a cheap trick is to just take 2 pipettes, stuff some crumpled up Kim wipe in the bottom of one, and then squirt your solution through that into whatever vial you're using for the crystallization. So you don't have to use an expensive microfilter or anything like that. So the Kim wipe works pretty well, actually. Or you can use, what's that called? That woolly material. Anyway, what you have around. Try to not have any insoluble stuff sticking in there, or powder, or hair, or anything like that. Hair looks very big under the microscope. Have you ever noticed? Just read that. Dust, filter paper fibers. You want to get rid of them. And also, if they're present, then there's just more junk when you're examining them under the microscope. If you consider what's happening when crystals grow, the shortest dimension of the unit cell is usually the direction where a needle will grow. Why? Because it's the simplest phase of the growing crystal. And so the nucleation to further grow takes place there. So if you're looking at some kind of interesting conductive material where you want to see where is the conductivity axis, it's often the needle axis because things stack up that way easily. And plates, correspondingly, they grow in 2 directions fast, but not in the 3rd direction. Okay, so sublimation, it just needs, whatever compound you have needs to be thermally stable. I already mentioned that. You can set up a pretty easy apparatus to try that. Now I'm going to tell you about the other method that I mentioned, which is the diffusion method. Okay, and I've had a lot of success with both of these methods, and there's variations, of course. So one of them is vapor diffusion. So in this picture, this represents the solvent-solute mixture. Okay, so you've dissolved your material in something, and this is a jar, actually. Better, or you could use parafilm to cover it, but jars are better, I think, because you really can get the lid on nice and tight. So this might be, let's say, for example, this is dichloromethane. This could be just ether, pure ether. Okay, let it sit for a while. The ether is going to diffuse into the dichloromethane because it's less dense, more volatile. And if it's a counter solvent, what we call counter solvent is something that your substance is insoluble in. It's going to slowly diffuse into there, eventually cause this to become saturated, and crystals will grow. Again, this takes patience. It doesn't happen really, really fast. But you set it on in a drawer or in a closet somewhere and forget about it. Check it. The nice thing is that this volume increases, and the crystals tend to not end up high and dry up at the top, although sometimes they do anyway. But they're still in the mother liquor, so they're not going to lose solvent. So the good solvents for the top are things that are more dense, and for this, more dense solutions and less dense counter solvents. So they'll vaporize. Pentane's good, but I'm warning you about pentane. Do you realize that if you buy drum pentane, it's only like 95% pure? Do you know that? Or hexane, I'm sorry. Not pentane, but hexane. So look on the container, but it also has in it a lot of this. Methyl pentane in the drum hexane. I think it has, maybe as much as 5%. But this can really complicate things. You look at this molecule and you say, I didn't put that in there. 5-membered ring, but it's in the hexane. So if you used hexane for crystallization, and if you can afford it, use spec grade hexane rather than drum hexane. We have a professor in our department who uses tons of hexane, and I see that a lot. And I'm always telling students, don't do that, but they do it anyway, of course. You might also consider drying the solvents before you use them. Sometimes that's important because water is something you don't want. Okay, so this is probably the most used technique in our lab, where we noticed this crystals grew in NMR tubes, so we got cheap glass tubing, the 3-foot-long ones. You must have those too here, just the soft glass, not the expensive glass. Cut them into lengths maybe this long, and fire polish one end and fire polish the other end so much that it's sealed. Okay, so you've got a bunch of crystal growing tubes. Fill about halfway with a fairly concentrated solution of your sample, and then carefully layer the counter solvent on the top. But don't just squirt it in, dribble it down the sides of the tube so it forms a layer. You want it to layer. And then cap it off, set it aside. We have some racks that we've made various ways. And just leave it vertical. And again, don't disturb it. And using this method, it's very easy to set up parallel experiments so you can see what different ratios were, different molarities. Usually the crystals will grow at the interface, like is shown in this picture here. And you can make the diffusion even slower by putting a third solvent in between those two layers. One thing that's worked well is glycerin, if you have glycerin. So it's kind of a thick solvent that will still allow this top layer to pass through and go into the bottom layer. But just a few drops of that. Very, very thin layer, only to slow down the diffusion if the diffusion seems to be taking place too fast. Not necessary most of the time. The good thing about this too is that it doesn't take very much material. Like just a milligram sometimes is enough, or even for some of our fullerenes, we don't even have a milligram, believe it or not. I mean, we can start with micrograms of material and get this method to work. And after you see some particles growing, then you can carefully lift it up, look at this under the microscope by just tipping it gently to the side. But you're not removing the crystals to look at them. You're just inspecting them to see if they look good yet. Okay, and if they don't seem to be quite big enough yet, put it back in the rack, wait a little longer. But they're still there. They haven't, fallen off, hopefully. I mean, some will fall off down to the bottom. That's to be expected, but don't worry about that. This is where the crystal growth is mainly taking place, and it's cheap, doesn't take much material. It's good it's easy to get them out too, because what you can do is just use a long pipette to withdraw down to about here. Then using the tip of the pipette, knock the crystals off the wall, let them fall down. With a glass cutter, are you with me? A file, cut the tube here. Make sure it's filled up again to the top. Carefully invert it. And the crystals don't come out, they just fall to where you cut it. Okay? And then tap it to your slide and the crystals come out. Just tap it. So meanwhile, they're always in the mother liquor, and you haven't had to scratch the sides of the vial to get them out. You can just, while there's still liquid in there, you just tap them and they fall down. It's very delicate. Now you can use the same method to actually grow your crystals by doing the reaction in the tube, and that's allowed. You know, you can have the two reactants separated, and they can be diffused together. Crystals grow as the reaction occurs. If they're less soluble than your reactants, you can even use the same solvent. They don't have to be two different solvents. You can also use this method to do co-crystallization, which I'll show you in a second. So you have lots of variations on this method. And the glass is so cheap that once you're through with it, you could just throw it away if you don't mind throwing it away. It's just cheap, soft glass. Cheaper than NMR tubes, for sure. Okay, so the co-crystallization method. You want to think about guests and hosts. With fullerenes, we do this a lot because there's a lot of good host materials for fullerenes, and you need usually some kind of host, or else it'll be rolling around and disordered. So you can put the guest at the top or the guest at the bottom. It doesn't really matter. What you're just achieving is, again, a slow diffusion of two compatible materials, and the crystals will tend to grow at the interface. So for example, fullerene, so carbon cage, in this case on the bottom, dissolved in possibly toluene. On the top, nickel octaethyl porphyrin, also dissolved in toluene, layered on the top. Okay, wait a week or two or three, and eventually some crystals grow, black, shiny crystals. And here's an example of a crystal structure. This was what we call endohedral fullerene. So it's the carbonate cage, 80 carbons. Inside there's a nitride, terbium-3 nitride. It's called an endohedral. Anyway, I'm sure without the co-crystallizing agent that I never would have gotten this structure. So the porphyrin is the key here. The porphyrin, the nickel octaethyl porphyrin, a lot of you know about porphyrins, so I don't need to tell you, it has these arms that can either go like this and like this, or in the case of fullerene, usually both arms will come up and just kind of cup the cage. This is a pi-pi kind of interaction, or maybe a dispersion interaction involving some of the hydrogens on the ethyl arms. But it's apparently very favorable, and actually we discovered this by accident, but it's now been widely used internationally, I have to say, by people who do this kind of research, because it's nickel octaethyl porphyrin is particularly stable, easy to get. It's perfect for this, and we're so lucky that it works. Sometimes you do see in the structures, you see some dimerization of the porphyrins across this way. But the nickel-nickel distance is too long for it to be a really strong interaction. But a lot of the interactions in crystals are weak interactions. So, this is obviously favorable. We often see this arrangement. This was with benzene also, and it's in the structure. Cool, huh? Yeah. You have to come to my seminar, I'll tell you. You can't just poke it in. You have to create the interior stuff when you make it. So the fullerene's made in a arc discharge apparatus using graphite rods as the anode and sometimes the cathode too. And then you fill the one that's producing the fullerenes. You core it and then pack usually an oxide inside. And so at the same time that the carbon is being vaporized, the other stuff is being vaporized, and some percentage of the product, which is just soot, will contain the endohedral contents. And then after that is a long process of HPLC and separation, because you get other products too. But yeah, that's how you do it. Pretty cool, huh? Yeah. But like, in a typical reaction, this will be not the major product, and again, you only get out a few milligrams at the most, sometimes micrograms. Yeah, but at the time we were studying fullerenes. One half of the group was studying these arc discharge methods for making the fullerenes. The other half was studying porphyrins. And we just put the two together. And what a wonderful success that was. We've tried other porphyrins, and there are some others that work too. Phenylporphyrins, not so well. Fluorinated ones sometimes. So for ionic compounds, you want to consider what the counter ions are going to be. And just think about it in terms of the crystallographer too. So some counter ions are going to be floppy, tend to be disordered, cause problems. Like example here was tetrabutyl ammonium for a cation. Those butyl groups, you know, like all long chain hydrocarbons, tend to be waving around a lot at the terminus at the end. We have used them, but it's a little bit harder to model. Tetraphenyl borate's pretty good. Tetramethylammonium's pretty good. So, yeah, just think about the crystal structure when you think about which counter ions you're going to be using. And there is sort of a rule of thumb that the counter ion should be sort of roughly the same molecular size as the main material of interest, because they'll pack more efficiently if they're nearly the same size. So if your molecule is really huge, you're going to have better success possibly if you use a large counter ion, possibly. Something to think about anyway. So this is, I think, a really cool thing, which I learned about from some collaborators in Iran, actually, because they do a lot of what they call proton transfer reactions. But before you do the proton transfer, you don't even get good crystals. So I'll show you in the next slide what it looks like. So you have a compound that's neutral, and it's a proton acceptor, say. So then you have a donor group that's a hydrogen donor. Then there's a transfer, and the crystal grows very well after the transfer occurs, because it's being stabilized by hydrogen bonding, essentially. So a lot of these reactions are done in water, but you can also carry it out by grinding, interestingly. You can take the two components, grind them together in a crucible, and or you can use a more advanced device. In a crucible, you have to grind for quite a long time, but eventually it will sort of liquefy, and then you just wait for it to grow crystals, and you come back and there's crystals there. Amazing. You never even used a solvent. Okay, so this is an example of how this might work. So you see the reactants on the left there, and then there's a proton transfer from one of those carboxylate groups, in this case, could be both, to the other side, and then the crystallization produces this, and there's all kinds of hydrogen bonding going on here, like from here to here, here to here. There's water incorporated too, so all of those things together, here to here, maybe stabilize this crystal. Gosh, I don't know, there's been dozens of these reported, maybe too many, but the point is well made, that this actually does work very well. So coming back to the crystal manipulation, before you take the crystals out of their mother liquor, make sure you're ready, because the longer they sit out, the more the mother liquor is going to evaporate, and pretty soon they're going to crack and stick to the slide, and you'll be sorry. So have everything ready, your slides, your pipettes, vials, oil. I like to just use sewing needles in what's called a needle vise for manipulating crystals, but people have different preferences there. You want to have a razor blade or something that's sharp nearby, because sometimes you have to do a little surgery on the crystals. They're stuck together, they're too long, things like that. So you learn to gently use a razor blade or some tool like that. And then you should have mounting pins ready, because as soon as you find the crystal you want, you mount it on a mounting pin. Usually, different labs have different things. I like these Mighty Gen loops a lot, but we used to just use a thin piece of glass. If you're going to use a cold stream, you don't need to worry about glue, because the crystal isn't going to move. Whatever that viscous fluid is going to solidify at low temperature, and it acts as the glue, okay? So you don't want the crystal moving while the data collection is taking place. If it's at room temperature, you're going to have to use glue, and that's a pain. And once you've taken it off the diffractometer, you can't really remove the crystal, so you're probably going to have to throw away the mount and throw away that crystal. But if you use low temperature, then you can just gently remove the crystal and reuse that mount again. So that's also an economical way to do it. But make sure that the previous user didn't leave his crystals on. So what you see under the microscope is usually it's pretty obvious right away if you have a good candidate. On the top there, you see some nice, pretty needles. On the bottom, you see some stuff that looks nasty. Probably those are just needles that have grown around a central nucleation point to form those discs. But they're not good crystals. You want a single crystal, and so you look at those and you say, no way. This bottom photograph, I can tell by looking at it, was done with polarizer filter turned on and rotated so that you see the background. Polarizer filter is very, very useful for selecting crystals. Have you ever used one on a microscope? Okay, so let me show you what the effect is. So what it is it's again just a polarizing filter. It fits on the microscope, and as you, because of some birefringence effects and stuff, as you rotate the crystal, you get what's called extinction, and it will look dark. And then you rotate it maybe another 180 degrees, and it looks light again. And this is a fantastic way to check for single crystal behavior. If it's not a single crystal, then you'll see more than one extinction, or you'll see no extinction. Certain crystal systems don't extinguish, like cubic crystals don't extinguish, so that won't work. But most monoclinic and triclinic ones, which are what you'll see, do. What you see is, okay, this is a good crystal. See it go light? I'm just rotating the stage underneath. And then it goes dark again. Light, dark. That's a really nice crystal. Sometimes the background looks completely black and not purple, but I think this is just the way the photo was taken. Let's go to the next one. This was a bad crystal. Here we go. Already it looks suspicious because you see it doesn't look clear, it doesn't look smooth, it looks like there's, I didn't realize we had audio. That's Professor Hope talking. He took these pictures. Okay, you get the point though, right? Yeah. So if you can find somebody with that kind of a microscope, polarizing microscope, it's a really good way to look at crystals. I got a sample from Todd Harrop. Some of you may know who he is because he worked for Pradeep Masharak and does bio-inorganic chemistry. Sankar definitely knows him. So he's a professor at the University of Georgia. And he wrote me an email and he said, my crystallographer says these needles are too fine. Do you think you can do anything with them? And sure enough, you know, he sent them. I looked at the sample. They were very, very fine needles, probably too fine to do in our home lab, but I could tentatively take them to the synchrotron, which is where we take small crystals. But I looked at them under the polarizing microscope, and among those thin needles were some bigger crystals, but because they were colorless, they didn't see them. You could only see them when you saw them extinguished like that. And then I thought, well, those are big enough. So I got the data set and sent him the result in a couple days, and he was amazed. So again, I just can't emphasize enough how powerful that is. Don't waste your time on bad crystals. Try to get better ones if you can. Take it as a serious part in the whole process. Try a lot of different things, and you know, if possible, learn how to mount them yourself. It's really a skill, and it was rewarding because you get something with beautiful diffraction pattern, and you know that's a keeper. But if you see one that has an ugly diffraction pattern with lots of streaking and possible twinning and stuff, reject it. Try another crystal. Patience is the key. Patience. Okay, so I think that's my last slide here. Oh, okay. Here's another one. Okay, why do you need good crystals? So precision, higher quality crystals give diffraction to higher diffracting angle, which is the same thing as better resolution. It's inverse. Remember Bagg's law? D is the resolution. So higher diffracting angle, lower the value of the resolution. So 0.833 is supposed to be the cutoff for good resolution. That's about 50.5 degrees with molybdenum radiation. But if it diffracts to higher angle, then you should collect that data too and use it. Don't just cut it automatically to this resolution. Some of the structures I'll be talking about this afternoon, we could never do without resolution of maybe 0.6 angstroms because of disorder. So in the end, you'll be thankful that you have taken the time to grow a good crystal. Oh, this is cute too. So one of the faculty in our department, Bill Casey, who studies earth and water kinds of compounds. So this was an aluminum hydroxide. The crystal structure appeared on the cover of, Inorganic Chemistry. It was a really neat structure. It's an octamer of aluminum 8 hydroxide, water, sulfate, 16 solvent waters. It actually was pretty well behaved considering the components in it. But the interesting thing was the description of the crystal. We had already determined a structure of an aluminum dimer, and he thought that's what the solution was, but it had been sitting on his desk for 7 years in a beaker. And he handed me the beaker. He said, would you just make sure this is the dimer? And the crystals had been growing a long time. They were no longer a dimer. They were an octamer. And we got this really beautiful structure. So that's the record, 7 years of growing. You can read that if you want. It's kind of an interesting synthesis. Okay, so that's the end there. Let's see what, I would really appreciate it if you would contribute any successes that you've had in growing crystals. How do you usually do it? Do you do it in a Schlenk flask ever? Do you use Schlenk flasks? You know what those are? What do I use? No, usually we have so little material, I just use the thin tubes. But Phil Powers' group uses Schlenk flasks because their things are very air sensitive. So what they'll do is they dissolve, they'll usually just take the reaction mixture, actually, because they don't want to deal with removing the stuff, separating it, purifying it. That's okay, it actually works out. So they'll warm it up until the material is pretty well dissolved, and then they set it in a dewar that's large enough to accommodate that Schlenk flask with perhaps ethanol or something like that surrounding it, okay? And then they just, so the Schlenk flask is warm at this point. The ethanol in the dewar is going to cause it to cool slowly. So they allow it to cool slowly to room temperature. If anything happens, maybe we'll grab some crystals then. If nothing has happened, they put it in the refrigerator, let it cool further, slowly, because the dewar is still there with this liquid. You follow me, how it looks? Do you understand? So, should I sketch it? Okay. So Schlenk flasks are kind of these funny looking things that have stoppers in them and everything. So then surrounding that is the dewar, which will have some, say, ethanol in it. And there's reaction product is here in some liquid. So they warm it up till all the crystals have dissolved or the substance has dissolved, and let it sit and come to room temperature with this dewar around it that makes it cool slowly. And then if that doesn't succeed, cool it in the refrigerator, and if that doesn't succeed, cool it in the freezer. The reason I don't like this is it's very hard to get the crystals out, but with a long, thin spatula, you can kind of scrape them out. But it's tricky. It's much easier to get crystals out of a thin tube or something smaller, like a vial that's that size, kind of. Plus, usually somewhat short on time because your stuff is air sensitive. But that's one way. That's another way. Anything else? What do you use? I didn't quite understand. You can say it one more time. Oh. Mm-hmm. Yeah, that's right. I didn't mention that. Gel crystallization. I have seen that. Mm-hmm. Yeah. I tried it a few times. I didn't have any success, but it's cool. Yeah, that's a neat technique. Yeah, but getting the crystals out is hard. Yeah. You can't just like distribute it on a slide and then pick them out with a needle or something like that? Or is it too thick to do that? Have you tried getting them out? No. What?
He's asking that how to get the crystals from there. He's not getting crystal in that gel compound.
Mm-hmm.
He's getting gel. Not crystal.
Too bad, yeah. Yeah. Again, if you can use the polarizing microscope, though, and spread it out, you can spot a crystal because it'll be the part that extinguishes. No? Doesn't work? Yeah. Okay. Mm-hmm. Yeah. You want to sketch it so I can see what you're doing? Go ahead, come on up. If you make a picture, it's clearer. Here. Mm-hmm. Mm-hmm. Uh-huh. Uh-huh.
So when you do that, after some days, we got some change or single crystal.
Oh, that's what came out. Uh-huh.
Yeah.
Mm-hmm.
So what will be the reason and how to get rid of these things? That I am asking.
Mm-hmm.
We are looking for single crystal, but at the end of the day, we are getting some type of gel type compound.
Mm-hmm.
So what
Yeah.
may be the reason that I am asking?
Sort of colloidal stuff. I don't know.
Actually, in some journals I saw that from that gel compound they had added some counter anion or counter cation from outside.
Yeah. And then it would dissolve in that and then leave behind the crystals.
Get the crystal. So
Yeah.
I'm asking that what is the reason for getting
The
that
gel. Why does the gel form? There must be something in there that's making the gel form. Just like when you cook and you make Jell-O or something, right? Yeah, I don't know. Can you rinse the gel off though with something, some methanol or something, or not? Yeah. That's nasty. Maybe it's too concentrated. If it's not working, try something else. I don't know what else to say.
to change the solvents like this?
Mm-hmm. Yeah. What solvents are you using here?
Any solvent is not fixed that what this solvent the gel will come, what this solvent gel will not come. It may come, that I am asking. So in some of the reactions I got some change, so that's the thing I am asking. It's not fixed with some liquid solvent.
Okay. So is it possible that your material polymerizes in some way? You're forming a polymer?
Maybe or maybe.
A nanomaterial? I don't know.
I have no idea what is making it.
Yeah, if it's a gel, then it's probably not anything that's ordered. It's, yeah, right? So, yeah, I don't know. Did you talk to your boss about it? I'll tell you another curious thing that I discovered was when I was looking at these diamondoid things, which are just hydrocarbons. They're very soluble in Proton oil, which is the oil that we usually use for examining crystals. So I would put the crystals on the slide, put Proton oil on them, and they would disappear almost immediately. They do dissolve in the oil. So I found in my cupboard in the kitchen some Caro syrup, which is a thick, sugary syrup. Do you know what Caro syrup is? It's like, it's a product that's used for making things in the kitchen anyway. But it's basically a polymer of sugar. So I thought, okay, so if it's viscous and it's sort of like oil, it should be okay. And that actually worked fine. It didn't dissolve the hydrocarbons because it's a carbohydrate. But Proton oil is another hydrocarbon, so of course it dissolves hydrocarbons. Yeah. From air sensitive? Carefully. Let me think. So, what kind of container are they in initially? Just a flask? Glove box is one way. Definitely a glove box. Another thing I've tried is bubbling nitrogen through and then capping it so that the nitrogen is the gas and not air. If you could get some nitrogen. How about that? Just bubble some nitrogen in for a few minutes and then cap it to get rid of the air. Or glove box. Yeah. Glove box, a lot of people use glove boxes. Mm-hmm. Then you have to deal with the glove box. But, yeah. Mm-hmm. Mm-hmm. Yes? Mm-hmm.
And even you're changing the solvent systems, even though if it will be like that means
it just gets powdered.
Yeah, and after some time, after a few days, after a few months, it will be getting dissipated. How we can minimize? If we for the layering, for example, we cannot go behind the 2 or 3 solvents.
Usually that just it means you need to try a different solvent system, I think.
Only that is the way.
Unless you can use a seed crystal, if you could get a seed crystal, or crystals, put the seed crystals in, that might help. You know, it could be that though it's just getting shook too much. You know, put it someplace really quiet so that the crystals go slowly. Try different concentrations. We really just have to set up a lot of parallel experiments to see what works. Yeah, I know it's frustrating when you see that. But if you do have a precipitate, you haven't lost your compound, so you can recover it, start over, right? Yes.
Technician try 1 or 2 of them, and they are not giving the spots. So they should try all of them, or they should assume that this will not work. Because most of the time it happens that technician check 1 or 2 crystal and say it will not work.
Yeah.
What should they do?
It really depends on the limits of your patience and of his patience, I guess. Yeah. After some experience, you can look at them and say, these are never going to work, you know, but it just takes some experience. If they all look kind of like globs rather than crystals, maybe it's never going to work. But if they have nice flat sides, they look like a crystal. Maybe not hope is lost, but if they look round like that, they're usually not crystalline. So, yeah. Sometimes though, like I said, you know, they lose solvent, so in a few minutes they could be bad if you let them sit out too long too. Probably not. Yeah, they're probably all pretty much the same. Yeah. I'm very patient. I usually try 5 or 6 crystals before I give up. But it just depends how they look, too. You want them to probably be, for a home diffractometer, a minimum of like 0.2 millimeters on the side. If you go to a synchrotron, because of the increased flux of the source, they can be easily, 0.008 millimeters in size, and you can still get a good structure. So that's the advantage of a synchrotron source. Also, these latest microsources that they've come out with, you can use smaller crystals too. But if it's a tube source, at least one dimension probably has to be 0.2 millimeters. Otherwise, they're going to be too small. Yes.
People get microcrystals, lots of mutation is there. So what they can do to reduce this mutation point, basically what crystal parameters, what they can change to reduce these mutation points so that they will not get microcrystal but get the maximum.
Right. Yeah. Maybe filter with a smaller pore size to get rid of any possible particulate matter that's in there or leftover solid. That might help. Yeah. Make sure it's not being shaked. Like,
They change the temperature or something.
yeah, if you're cooling too fast also, that might make them too small. Make sure you're cooling slowly. And you don't have to have a Schlenk flask to do this method. You can set it inside a dewar and help it to cool slower.
And I see one slide, the bad crystal was there. Nucleation points were less, but still it's growing like CRG kind of lots of.
Oh, yeah, yeah.
So what is the solution? Oh, this might be not perfect solution, but what is it we can try?
Are they big enough that you can cut off a leg?
But they are not big enough.
Not big enough. Yeah, yeah, yeah. Yeah, that's a tough one. Some things just do that. But still, I think you really have to be sure your glassware is really clean and that there's no particulate matter left in the solution. They sell these pretty expensive filters that you can use if your particulates are very small. Maybe you can convince your boss to buy some of those. I forget what the size is, but you can go really good crystals that way. Which group are you in? Are you in Pradeep's? Oh, you're one of the technical people. Oh, okay. Yeah. So, I don't know what the answer to that is. Sometimes you have to just keep trying. And if it doesn't work, give up. Some things will do that just naturally, and I don't know how to avoid it. Yeah. Uh-huh. Yeah. Uh-huh. Yeah. Mm-hmm.
What are the ways or parameters we can do in the quality data from that where we can get the
Mm-hmm. Uh-huh. On the instrument, there's usually if it's like a Bruker instrument, which is the one I'm used to, there's a circle thing at the top, and if you drag that across the screen, it gives you the resolution. It prints out the resolution, and again, you want to have 0.83 angstrom resolution for it to be likely to be a publishable quality. And if it seems too weak at that, whatever speed you're using, you can slow it down. Collect, like frames that are 30 seconds instead of 10 or something like that. Mm-hmm. Mm-hmm. Right, right, right. Low temperature.
Sometimes you may not get the crystal.
Mhm.
whatever you got.
Mhm. Mhm.
Like we have rice,
Right. Right. Mhm. Yeah.
very good,
Yeah. Send them back to the researcher and say, try again. I mean, you have preliminary evidence that it isn't going to work, so don't push it, just reject it. Or be like Todd, who sent them to me and said, my crystallographer rejected them. Can you look? Yeah, interestingly, I have had crystals sent to me from around the world. And in some cases, they just put them in an envelope with some styrofoam around it and they arrive. Sometimes they're examined by the people at the borders, but I've received crystals from China, Iran, India, Japan, many places with no problem at all. And sometimes we have extra time at the synchrotron, so that's something to think about. At least for this coming year, we have time. I'm not sure if I'll renew it after that. Mhm. Okay. Again, the polarizing filter on the microscope will tell you right away if it's twinned, because as you rotate it, you'll see it blink, and then blink again too fast. So blink, blink kind of thing, instead of slowly regaining the color. That's one way. And the other way is when you look at the spots on the diffractometer, you see a lot of spots that are unrealistically close together. They should be separated, Again, it takes some experience, but if they're too close together, it's probably a twin.
Can you elaborate the differences in spots of proper crystallization?
Why don't I see if I can bring some images, and I'll show you some next week. Okay, if I can find them. It's not for sure that you will fail if it's a twin. Sometimes you can deal with it, If everything seems to be twinned, then I think you should go ahead and collect the data and see if you can solve it. It's possible to separate the twins by other methods, No, but if you don't have any choice, do it. Yeah. Some crystals, especially plates, I find. Crystals that grow as plates are often twinned. And you can't cut a plate this direction, It's too hard to get your razor blade in when it's really close together like that. A needle you can cut, but a plate, it gets really hard to get the two twins apart without destroying the crystal. So sometimes you just have to go with it. Yeah. Mm-hmm.
Some molecules crystallize very fastly and some molecules never crystallize.
Uh-huh.
Is it possible that for some molecules it will never form a crystal? Is it like that?
I wouldn't give up give them maybe 5 months or something like that. Yeah, yeah, really. Yeah. Maybe, okay, another thing you can try, of course, is you have your tube. That you've capped, say, and you've got these two layers, and nothing happens, and nothing happens, and nothing happens. If this is just a rubber cap, you could just stick a needle in it and make a little hole, or you could remove the cap and let it concentrate a little bit more. That sometimes helps. So, yeah. I wouldn't do fast cooling. I wouldn't cool it immediately in an ice bath. I would cool it slowly if you're going to cool it. Mm-hmm. Yeah, those are difficult. Mm-hmm. Mm-hmm. Well, I like that dry ice method I described, where you take your petri dish and put dry ice all around it. So crushed ice, dry ice, and then the slide here. So ice all around. So it gets cold pretty fast. And then if you put a little puddle of your crystals in your mother liquor in the middle, it gives you another few minutes to get the crystal out. Yeah. That's an easy way to do it. But yeah, DMF and Yes, that goes away pretty fast. Sometimes crystals don't have any solvent in them, sometimes they do. Hard to predict, yeah.
If we try 100 possibilities, then anything can crystallize?
They tell you that, but I don't think it's quite true.
I'm asking because, say like that, some compounds have no crystals. Is it right or?
I guess, so like nanomaterials sometimes never really form a crystal. They just form globs. If you look at them with an electron microscope, you'll see there's nothing that looks like it has edges, no straight edges. They're just globs. And that's because basically that's what they are. They're nanoparticles, right?
If the compounds are supposed to be 24
Mhm.
I'm not talking about them.
Okay. Yeah. Do you ever see powder that could be microcrystalline? If you see a powder that looks like it could be microcrystalline, then they are crystallizing. They're just crystallizing small. Do you have a powder diffractometer? You can check that way with powder diffractometer. Yeah. Sometimes you can even get a structure with powder, but it's hard. Yeah. I hear your frustration. I know it can be hard. Yeah. Sometimes it just doesn't seem to work. Or you've used up all of your sample and then it's gone, So, yeah. So, yes. Yes.
So they can they use seeding techniques small ones because people don't have to also, but and if they can, how they can use it better?
I haven't done it much, but it seems to me you should be able to just drop some seed crystals in and hope that it will work.
Just take press it and take some part, take the solvent away and solve it.
Yeah. And even though, okay, here's another thing. Even though we say get all the particulate matter out of there, get all the hair and the dust and everything out, I have seen crystals grow on pipe cleaners very nicely. Do you have any pipe cleaners? There's an experiment I do with children where we use pipe cleaners and they grow these big, beautiful crystals on them. So then you can make shapes. I'll send you the formula for this. You can make beautiful shapes. It's just using borax. Do you know what borax is? It's something that you could put in the laundry soap. It grows really big crystals. So you just dissolve the borax in hot water and then hang a pipe cleaner into the beaker or whatever. Overnight you grow huge crystals. It's amazing. And they grow on the pipe cleaner. So then you can like make your initials or something and then pull it out and all the crystals cover it. It's very beautiful. So, and why this happens, I have no idea, but sometimes I have grown crystals where there was say a transition metal compound in with what I want, and that it doesn't end up in the product crystal, but it helps the crystals to grow. So there's something about its compatibility with the growing crystals that helps them to grow. This is hard to understand, and I don't really understand it at all. If we could watch it, we would maybe know. But we can't watch it. Just have to hope. Yeah.
All of these measurements for the small ones,
Mhm.
what would formulate, like what methods?
Yeah, it's sort of the same methods, I think. But there's problems, of course, because you're going to get these cavities, and then you have all the disorder in the cavities. Over in Berkeley, there's a lot of people doing metal organic frameworks, and maybe you should talk to those people, get their advice. Yeah, it's find out who the people are who are working with, what's his name, the guy? Who's the guy at Berkeley who's famous? What, say it again? Omar Yagi, exactly. Yeah, he's faced these problems for many years, and so my ex-graduate student who works at the synchrotron works with him too. And she might know something that she could advise you about, what works and what doesn't work. Seems to me you really want to use something that isn't going to just completely disorder in the cavities. Water is probably bad, but on the other hand, water will hydrogen bond, but maybe not in a systematic way. Yeah. I'll ask her, see if she can give you a contact. Yeah. I know Omar Yagi is very hard on his crystallographers and his students. He gets very angry when they can't do it. He has a bad reputation that way. But I sympathize because I think it's inevitable that you're going to have a big cavity and you're going to have stuff inside that doesn't order. They do some really cool experiments though, where they put different gases inside, and then take the gases out. If it's a reversible process, see what happens to the structure. That's interesting. What else? So I'm killing time too, because somebody's going to pick me up at 11:30. So, yeah. Any other tips or observations? Okay. You're not getting any what? But it's not making the polymer, or it is? Strangely enough, I've heard of people using, what is it, like 100% acetic acid, what's it called? When you use pure acetic acid as a solvent. Have you ever heard of that? Glacial acetic acid. Yeah, so it doesn't contain water, it's just the acetic acid. Sometimes can be a good solvent, strangely enough. Glacial acetic acid. But yeah. I did one, do you know what Proton oil is? Do people here use Proton oil too? It's very common. It's a long polymer. I did one structure once that formed a very stacked structure, and these chains of Proton oil were incorporated in the crystal structure. Just there was a space there for it, so it got in there. It's just really hard to predict what's going to happen. Okay, well, if there are no further comments, you guys can go, and I'll just hang out for another 5 minutes, and I'll be here.